Back for part 3. This is Larry Benko again, W0QE. This is the third video in the group I was doing on analyzing a circuit under real-world conditions where the generator has harmonics in it and the load is of many different possible impedances. Before I get started doing this, we have to pick a filter we're going to use. The example I'd like to use would be a let's just say it's a legal limit solid-state amplifier for the amateur radio community. And to do that, we're going to need a low-pass filter on the output of it. I've got 3 selected low-pass filters here in this SimSmith file. They're all considerably different. They all have different merits. We'll pick something like one of these, or we'll pick one of these. But in the meantime, I thought I'd just go through a little design process of doing this and mention another new feature in SimSmith. The first filter let's look at is a very simple filter. It's a third order low-pass filter with a capacitor across the inductor here. It doesn't match any topology that, you know, any kind of topology like a Chebyshev or a Cower filter. It's just homemade. It's homemade by taking the components, moving them around in SimSmith, and see what we get. And if we plot that filter, that's this one right here. So we're going to look at the power going into load LG2, and we're going to look at the impedance at U3. And all these filters are designed to be 20-meter filters, and they have to match the FCC requirements. The FCC requirements are 43 dBc or better at all spurious frequencies. And we're going to assume our amplifier is stable so it doesn't produce any spurious frequencies, but it does produce harmonics. So we have a 1-watt generator here, and it's a standard UZ0 output. The load is 50 ohms, so it's the best case here. And that's how the amplifiers are tested, by the way. They're not tested with a 3-to-1 SWR for measuring harmonics or anything. They're tested with a 50 ohm load. We have a plot here of our output amplitude, and we can see that our fundamental frequency here, we have about 1/10 of a dB loss. And that's assuming an inductor with a Q of 200 right here. We have a fairly narrow SWR passband here. And if we assume that this line right here at 1 point, I think it's 1.25 to 1 is where all we'd ever tolerate for our generator, this would cover a range of 13.166 to 14.35 megahertz. I didn't exactly center it in 20-meter band, but we can get the idea by doing this. This circuit with this big capacitor here, when I say big, it's fairly significant, means we cannot use this as a low-pass filter at anything other than the 20-meter band. The loss we see up here is due to mismatch loss due to this SWR. Our second harmonic is 27.5 dB down, which is not 43 dB. Our third harmonic is 38 dB down. Now, the rules do not require us to have 100% of the rejection be done in the filter. The amplifier is capable of being clean enough to not even need an output filter. So if we assume, and it's a fairly typical assumption, fairly good assumption, that the second harmonic on a solid-state amplifier, due to the symmetry in the typical topologies we see in LD MOS amplifiers, we should probably have a second harmonic that's down 20 dB easily. So if it's down 20 dB, and we get 27 more in our filter, we're at, say, 47 plus dB down, and that beats the requirements by 4 dB. That might not be adequate enough, but this is a fairly simple circuit. It does work. Our third harmonic is 38 dB down, right down here at the bottom, and typically the third order harmonic on a LD MOS amplifier is pretty bad. It can be as bad as maybe 13 or 14 dB below the carrier. So 13 dB on top of this gets us 51. And 51 is good enough below the 43 to be good. So we could say that this circuit is actually an acceptable filter. Very few people build this filter in an amplifier for a couple reasons. One is the inductor current is higher than these other filters. The other reason is the capacitor currents are higher. It's a lot harder to get the parts. But as we'll see later, that's neither here nor there. It's a choice. It's a possible filter to use. The next filter I'd like to look at is a fifth order Cauer, or what used to be called elliptical filter. 1, 2, 3, 4, 5, fifth order, and both of the inductors have capacitors across them. This circuit is very similar to one that Jim Tawney has in his program Optimum Low Pass, and he has a set of filters that are used for each of the individual bands. And if we look at this filter, it has a slightly different characteristic than the simple filter did. So it's the filter down here. So we want to look at the output, power at the load. We see much better suppression at the 2 harmonic frequencies. It's been tuned for those, of course. And we want to see its SWR at U1. So it has a much nicer SWR area here, although we still can't use it as a low pass. We still can't use it on all frequencies below 20 meters. If it was intended for a single band filter, it would be quite good. It has a higher area where it rolls off than the simple filter did, which is again good. It gives us more tolerance to component variations. It will end up, as you'll see later, has lower inductor currents than this filter had, which is again good. And it has extremely good rejection at the second and third harmonics. So it doesn't matter what kind of a transmitter we put into this. This transmitter can be putting out an absolute square wave, and this circuit would be plenty good enough. It could be doing anything short of having the harmonics be higher than the amplitude of the input. We get 70 plus dB there, and this one doesn't even show. It's 90 dB down, if that's even accurate. These nulls, by the way, are never achievable in practice when you get that deep. Stray capacitances and stuff get in the way, but what you can see from this circuit is much, much better. Also, it has more components. It has an extra inductor, and it has 2 extra capacitors. And every bit of componentry costs money. Inductors cost money to wind. They cost money to get their board space considerations, etc., etc. And this is another choice. The last one is kind of an interesting choice, and it's going to, let me just close this off. We'll bring that up. It's kind of funky here. SimSmith has a new feature where SimSmith will actually build a filter for you. It's kind of, let me say, it's not ready for prime time really, because it requires you to build a circuit that you know is going to be the topology that this process will populate. So if that makes sense, I build this circuit, then I tell it it's a Chebyshev filter. It's got a ripple value that I can specify up here. It's got an impedance it's going to run at, which I can specify. It's of low pass type, and these are the components that are in it, and yet they have to be ordered in a certain order. And the outside component is a shunt component. You can also build this Chebyshev low pass filter with having 3 inductors and 2 capacitors, in which case the two outside inductors then are in series. So this tells us the filter. This is the downside in using this function. The downside is I have to practically design it myself to get it to populate it. Now, if this is a popular feature, maybe Ward will come up with some additional help where he'll populate the, he'll draw the circuit based on what this is and things. But it really doesn't matter. This is the beginnings of something that might turn out to be really nice in the future. And a lot of other features, early features in SimSmith, actually did just that. There were a lot of features that were there. They laid around in kind of a state of semi-completion for a while, and eventually they got tweaked on a little bit and ended up being very, very nice features. So this feature may be the same way. Nevertheless, I ran this. Let me make this a little bit smaller here. I did this. Well, let's basically do it. I'll comment this out so it doesn't run. It doesn't change anything when I do that. Let me change some of these components here. to be different values. You see I've changed C8 and L7. Now let me run this again by removing the comment. Let me close this off. And it's repopulated those. Now, let's look at that filter and see what the qualities of that filter are. We'll look at it in addition to these others. So it has, the load we want to look at is at LG1. It'll be red. It's between this filter, the simple one, and between the optimum low pass filter, which was the Cowher filter. And its SWR is at U2. So it has a very nice feature in that it's designed to have good SWR all the way below the cutoff frequency. So it could be used, say, as a 30 meter filter also, provided it gave me enough harmonic suppression at the second harmonic of 30 meters to be acceptable. In this one probably does not, but you might be able to tweak on it and make it happen. Nevertheless, if we look at this a little more closely, what we see is we can control the frequency and the ripple. If I make the ripple larger in a filter like this, we will see our stop band get better. We will see our pass band get worse. So let's change the ripple here. I'm going to change it from 0.05 to say 0.2 dB, which doesn't seem like much ripple, but watch what happens. Pass band SWR came up significantly. Stop band got better. This may still be an acceptable filter to you. It doesn't really matter, which one you pick here. They probably both are similar. Change the components, of course, to make this happen. But what we see in this filter, this fifth order Chebyshev filter, 2 inductors, 3 capacitors, lower inductor currents than this filter, which is nice. A fairly narrow pass band. So the wide pass band one was this filter. And, well, you might say this one's got a wider pass band. It ultimately has a much wider pass band. But, I mean, the really good pass band area was better with this filter. So we have to pick a filter. And for this purpose, I'm going to pick something that's similar to one of these. But I just thought I'd run through this real quickly and let everybody see what's going on. I've got a ton of graphing here, and I'll go through this real quickly. Let's turn off all of the SWR and power plots. And let's just look at I got everything off, okay. Let's change the power here to be 1500 watts. And the way I made this be 1500 watts and control the power is by this function right here. SimSmith allows you to put the power in parentheses in the construct that sets the type of the generator. So now I have a 1500 watt load, and just for grins, I'm going to look at the power here at L. We see that it's no longer 0 dBW. Let's go to watts for a minute. And we see it's 1.46 kilowatts, meaning 40 watts was lost in this filter. And that's pretty typical of a filter like this. The inductors will actually have power in them. So turning that off, if I look at this filter and I start to plot the components, this is kind of cool. I can plot the capacitor current at C1. I can plot C2, L1, L2, C3, C4, L4, and C5. Those are all 7 of the currents. Now, the highest current that flows here is this one right here, which is C3. This is pretty typical of these filters. This inner capacitor generally has more current than the outside capacitors, and it's 11 amps. It's 11 amps with a 1-to-1 SWR. It's going to get worse than that whenever we, in the next step, when we apply variable loads to this type of a filter. But the 2 inductors are right here. This one right here. Let me get around the spot there. L2 and L4 both have a little bit over 10 amps. And we don't care what the current is out here because you're never going to actually produce 1500 watts at 28 megahertz. So that's all we really are looking for is in this area right here. because that's where we intend to be using this. We will have a signal here, but it'll be 20 dB down, and the fact that it's 20 dB down from 12 amps is a tenth of the current, so it'd be 1.2 amps. So these numbers aren't too important. These are what's important. Another thing that's interesting here is I can plot the power in the two inductors, and I'm plotting them on the same curve as I was plotting the other power before. Make those go away. So what we see is 20 watts is in one of the inductors. That would be PL2, L2, and L4 has 16.6 watts. 20 and 16.37, something like 37 watts here. And the 37 watts that we have here basically is when we did the load here before, we saw 1.46 kilowatts. I said it was 40 watts lost. This is 36 or 37 of them. So those two inductors end up having 20 watts in them. If they're one on ferrite cores, you have to be a little bit careful. That 20 watts probably needs some air blowing by it to be okay. And we could do the same thing again, but let me go all the way to the other extreme here for a moment. Turn all those off. And let's look at these components down here. C11, 12, inductor 12, and capacitor 13. Oops. Instead of seeing 10 amps now, we see the inductor having 13 amps. You might say that's not that much of a difference. It's some. The capacitor now has 10 amps of current in it. The capacitors have a little bit more current than they had before. Inductor has a little bit more than it had before. You have to be able to make sure you can manage to handle that. Let's look at the power in that inductor. And we'll do that by dragging this down so we can see it. The power in the inductor now, single inductor, is 31.4 watts. The 31.4 is less than the two inductors before together, but it's more than either one of them. And this could be somewhat problematic in a ferrite core. In an air core inductor, it's no problem at all. But if this current that was here which was like 13 amps rose to be like 20 amps, we'd have to start thinking about winding it with something better than 12 or 10 gauge wire if we don't want the inductor to get too hot. So, anyways, this was a little lead in to the next section, and the next section we'll put the actual filter in there. We'll put the variable loads in there, the harmonic generator, and see what surprises await us. All right, this circuit should look familiar. We have the sweep scaler we used before. We had the file we loaded, which had 216 points of data. We scaled it down to a 3:1 SWR, which is how we're going to do our test. We're going to assume that the maximum SWR we want to face into the filter here is a 3:1 SWR. We also want to assume, for the moment, that we're going to run 1500 watts, and we're going to run 1500 watts with a harmonic generator. It's not turned on right now. We'll turn it on. A harmonic amplitude of 0.3 of the fundamental. That puts the harmonic 20 log of 0.3, which is 10.5 dB below the fundamental. This is a really bad amount of third order harmonic, and probably more than most normal amplifiers would have, but it's representative of somebody who builds a circuit and is pushing things. So this is probably a pretty worst case. And again, we're trying to size the filter accordingly. Another thing is, and I haven't mentioned this, and I did this work, and then I came to the conclusion that, as egad, this really is not right. What happens here is this sweep scaler is frequency independent in terms of its impedance. If we put a harmonic out here, it will have the same impedance as the fundamental has. What's the likelihood of that happening in a system? Well, if you're driving a dummy load, it's pretty good. If you're driving maybe some log periodic antenna, that the third harmonic is within the log periodic bandwidth, it might be okay still. But in a general circuit, it's not okay. In a general circuit, what you've got here is the third harmonic is going to see a wildly different impedance than the fundamental. So what I did is I put a circuit in here called a trap. And the trap has the ability to either shunt the harmonic or be open to it. And because of that, the third harmonic sees either a short or an open. And we can apply that based on a value we put here for switch. I did an earlier video where the switch command was used to basically connect circuits in it, parts in and out of a circuit. We'll come back to that in a minute here. In the meantime, I'm going to bring up the trap circuit here. The trap circuit is pretty simple, and that is I've got a shunt and a series circuit both. The series circuit here is the graph. We're going to look at the impedance right there, so it's LC1. So what we see is at the fundamental frequency, we see a good SWR. It's 1.1 to 1 SWR. But at the third harmonic, it looks like an open. It's very, very high. The other trap, which is this direction, which we see at LC2, again looks like a nice impedance at the fundamental frequency. I'm not quite on the right circles here, but pretty close. 1.1 to 1 SWR. And it looks like a short at the third harmonic. So that's basically what I built in that other ruse block. So we'll close that off for a moment and come back and look at this. So basically what I have here is this switch value can go between 0, 1, and 2. And what we will see here is the impedance will either connect this resistor. This resistor will either be 0 ohms, which will bypass this circuit, and this one will be infinity, or this one will be 0 ohms, and this one will be infinity, or both of them. Or if we can put, let's start again. If we want this to work as if it's not in the circuit, we'll short this one out and we'll open this one. If we want this one to have an effect only, we'll open this one up, and this one will be open too. If we want this one only to have effect, we'll short this one and open that one. And we can do that by, I'll do that in a minute here, but we just basically run this value up 1, 2, back, and you can see RS and RP changing as I do that. And again, these files will all be available. So 0 is the case, and I fixed it so if you go below 0 or above 2, it sets it to the endpoint. So here we go. I've got all these impedances coming into this circuit, and let's go here. We really probably ought to build this up slowly. This is incredibly too much information. The only thing I want to look at was what we saw, what I had before in the last video. I can look at the SWR, and the reason I put this circuit here is because we don't see this nice trailing off of the power due to mismatch loss here. We have all this circuitry in the way. If I look at U1, it kind of matches it, but there's effects of what the phase rotation is and everything else. So I put this in there as kind of like a buffer, and it will tell us though where things are going on in terms of SWR. So this was our first point, which is in the center of the Smith chart. This was our lowest SWR, our next lowest SWR, our next lowest SWR, our next lowest one, next lowest one, next lowest one, etc., etc. And the reason these lines get longer is because there's more points in those circles. This circle here only has 6 points. This circle has 12 points. This circle has 18 points, etc., etc. They go up by 6 each time. So let's look at the current, and I'm going to bring the filter back up here. Let's look at the current at C1. C1 is the component that will see the effects of the third harmonic for sure. We're looking at the current in C1, and we see the current varying. So at a match condition, the current sees somewhere, hard to see exactly where, it's hard to make it match exactly there, but it sees somewhere around 8.3 amps. And that's with a harmonic present. If we want the harmonic to be gone, all we have to do to make the harmonic be gone is get rid of this. Oops, have to get rid of it. So 8.3 amps became 7.6. So the effect of our harmonic was to increase the current in that capacitor by from 7.68 to 8.3. And you might say, well, that's not a big deal. But remember, power consumed in a component is proportional to the current squared. So we take 8.3 and divide it by, say, 7.6, square that number. We get it's about 20% more power produced in that, will be dissipated in that component. And we can do that for every single component in the circuit. So let's look at the current in capacitor 2. It's small because it's across this inductor, and the resonant frequency of this circuit is up above 14 megahertz. It provides the nulls in the stop band. We can look at the current in the inductor. It's higher than the current in the first capacitor. The current in the third capacitor, or in the middle capacitor, it's about equal to the inductor. The little capacitor across the inductor here, and finally the last capacitor here. Those are all the currents we see. Now, if we want to, we can look at the peak values of those, but we should turn on again. Let's turn on harmonics. And when I turn them on, watch here when I say done, and watch all the curves change. Some of them didn't change much, and some of them did. It's kind of interesting. And it really doesn't matter whether they change or don't change. I mean, it is what it is. This is what you get if you put that much, if you put basically a harmonic that's about 10.5 dB below the fundamental in. If I wanted to size my inductor appropriately, and I wanted it to work all the way up to 3 to 1 SWR, I got to find the biggest peak for my inductor current. The biggest peak for my inductor current is right there. And of course, instead of plotting this actual current out, I could have plotted just the peak, and that would have been fine too. But it's 16 amps. 16 amps in that inductor is really going to be, it doesn't need 12 gauge wire. It needs a lot more than 12 gauge wire on 20 meters or it's going to get warm. Let's look at the power in that inductor. And I'm plotting the power in the inductor here on Y2. So Y2 is its own axis. So let's make these axes go away for a minute. And there's the power. 40 watts is going to be in that inductor. We saw before the numbers were lower than those, but this is the effective SWR. The power in the inductor down here at low SWRs would be no more than maybe 22 watts. The difference between 22 watts and 40 watts, if we say that's twice as much, that's probably twice the temperature rise. So we have a way to size the component now. Now the beauty of this is, I mentioned this in the last video too, is if somebody comes up and says, okay, I'll change my specs now. I don't need this. I don't need it to work this badly. I only need it to go out to here. All I do is change my sweep here. And let's look right here and see what point we're at. That's 168. So let's just go. Let's take this. We'll save it for future use, but we'll go to point 168. This is hard to do on the fly without making mistakes. Watch what happens down here when I click done. I only go to 168. So now I would say 37 watts, and I would say my current, turn that one off and bring these back to a reasonable value again. My 16 amp current became 15.6. I didn't save that much. But it continues to get better as you go down with SWR. So this gives me a really easy way to look at something, and if somebody changes their mind, I've already got the data done, which is kind of really interesting. I think this is an incredibly powerful feature in SimSmith. Now, we mentioned before, let's go back to where we were plotting before. We mentioned before that we don't know what impedance the third harmonic is. So let's run this through the possible gamuts here and see what changes in our current. This current right here is sitting at 16.3 amps. It rose a little bit from 16.3 to 16.5, and there it dropped a little bit. So it turned out the third harmonic didn't really affect things much. So it started at 16.3, it went to 16.5 and down to 16.1 based on whether the third harmonic was the impedance down here that we're giving the fundamental, or whether it was a zero or infinity impedance. Some of the other components, I'll switch back and forth here between these and just look at this as I'm switching back. So this is position 2, position 1, and there's filter out. So we see certain components change and other components don't. You might say that this isn't very much of a change, and maybe that's what you should take away from this, that the impedance at the third harmonic doesn't really make much of a difference in terms of the stress on the components. Maybe you should take away, let's look at C5, and let's look at C5 by itself. C5 is at the end of the filter. You would hope that by the time you manage to get to C5, that the effect of the harmonics really don't make any difference. There shouldn't be any harmonics down here. That's the purpose of the filter, is to get rid of the darn harmonics. So let's go and look at this. Here the maximum occurs right there at the end point. So we'll look at that, and that's 9.8 amps. If we go over here and we turn the harmonics off by commenting them out, or we could have put a 0 in here, it wouldn't have mattered. It didn't change at all. Let me click on it again. 9.8, 9.8 again. Well, surprise, surprise. This component, if it's already at the end where the harmonics have been pretty much reduced to nothing, it shouldn't see a change based on harmonics. It does see a change based on SWR though, but not on harmonics. So there's a lot of interesting things. By playing around, you can really get some interesting, you can glean a lot. It turns out I made a comment when I've been just as well off to have swept this impedance right here with nothing more than a piece of transmission line attached to a 3-to-1 SWR. And from what this shows me, the answer is yes. None of these impedances back here gave me a value larger than what I saw in the biggest step. Remember, everything in this step right here is the same SWR. So there were no cases at all where the values back here were higher than the values at the higher SWRs. So the answer is we really don't need to do this. This is very cool. It looks nice. It gives you the ability to very quickly chop off part of this chart and have the answer still, but it doesn't really, all this data down here, if this is where the test is going to be performed up here, then that's the requirement. Then that's what we have to size the component for. Anyways, I thought this is kind of a. I may be easily impressed, but I thought this was very cool and a really valuable use of SimSmith. And I've had a few people who have come to me and asked me if I would analyze some filters. They weren't all amateur radio. One of them was an ISM band application that was running 15 kW. And doing these analysis are kind of interesting. You get to see that all the parts in the filter certainly are not heated up the same amount. There's no question about that. And they need to be sized accordingly. And in the cases I've been able to look at, people size the components all equally a lot of times. Every one of the capacitors in this filter would be the same size, where it becomes pretty obvious. I'm not plotting power right now in the capacitors, but if I just look at the current in the three big capacitors, which are capacitors 1, 3, and 5, I see that clearly this capacitor, which is C3, has 16 amps of current in it, where these other ones have 11. This capacitor will have over twice the power 16 divided by 11 and square that, that's a little bit over 2. This one will have twice the power. This will see twice the temperature rise that these will see. And if I'm a little bit naive about how I size things, that middle capacitor will probably be the most likely capacitor to blow up. Anyways, hope people found this interesting. Again, these files are pretty complicated. I will put them on my website. You can download them and play with them to your heart's content. And if you find this stuff interesting, let me know. If you have any other ideas for some videos, let me know also. I've got one more video planned here. It's going to be circuits that I use a lot in SimSmith. And there's a few circuits I keep coming back to over and over and over again. And these are circuits I actually have hardware equivalents of, and I'll have pictures and stuff of those. But I have a tendency to do the videos on things that I do myself. They're things I'm interested in. Other people are interested in other topics, of course. So I probably haven't touched on those things. So if anyone has some suggestions, that'd be cool. If not, when I come up with something new again, I will do another video. In the meantime, please subscribe. It'd be nice to get, a few more people interested in this stuff. Maybe at some point in time, we can write something, get a little blurb in QST or something, which will direct people to some of these videos, and maybe we can get some more interest in SimSmith, because there's a huge amount of power here that can be used to analyze some pretty basic electronics. But this is stuff that just wasn't available not too many years ago. It would take a huge amount of programming and a lot of effort to do what we just did in this video. Thank you very much again, and I've enjoyed this. This is W0QE 73.